Okay, so today we will continue our discussion of the simple linear regression model. So we're going to cover two main things today. We're going to talk about how to use the model to do prediction, and then we're going to work out an example on a data set, and we're going to do that on the board, and also I'm going to show you, introduce to you how to do that in R. Okay, so let's get started with prediction. So the prediction for this simple linear regression model that we fitted. Okay, so the idea is we want to suppose we we have a new value of x, and we want to predict y for it. So let's set it up as follows. So suppose we want to predict the response y for a new value of x. And just for concreteness, we will we'll say the point is x is the value, let's say at x0. Okay, so let's recap what the model looks like, and then we'll see how to do this. So first, so the simple linear regression model would say this. Okay, so let's remind ourselves of the form of the model. So okay, so we're going to need another random variable here since we're talking about the model. So I'm going to call this capital Y sub 0. So this just means the response for y when x is at this value x0. So let's call this the random variable for response. When the value of x is this new value here, x0. Okay, so that's the random variable for the response. So we're kind of thinking it of as the pair x0, y0. Okay, so according to our model, this has a normal distribution. Okay, so the mean of it would correspond to the value of x0 at which we want to do the prediction. Okay, so the model says it's going to be beta 0 plus beta 1, and then specifically x substituted at the value of x0, and then variance sigma squared. Great, so that's what the model would look like based on what we'll be talking about in these few lectures. Okay, so that's the model, and then we have fitted the model from n data points. Okay, so we have last time we talked about our estimates on beta 0 hat and beta 1 hat. Okay, so once we have those estimates, we can calculate the predicted value, which the natural one is simply to take the value of the regression line at the estimates. Okay, so let me write that down and then explain it. Okay, so that's the model, and so based on the fitted model, predicts the value of y. Okay, so I'm talking about the value here, so I'm going to use the notation lowercase because I'm going to calculate the value of a prediction from the data. Okay, and the sensible one to use, well, is you predict the value of the regression line at x0. Okay, so we plug in our estimates for the betas, so beta 0 hat and beta 1 hat x0. Okay, so based on our estimates, we can calculate this and we get a value for y0's predicted value, that's called y0 hat. Okay, so why is this a sensible way to do it? So in order to I mean, intuitively, it makes sense because our best guess for what the new value of y would be to simply guess the value at our fitted regression line. Okay, and that's this one. Okay, but mathematically, why does that make sense? Okay, so in order to do that, again, we're going to have to look at y0 hat as a random variable. Okay, so as a random variable, then. Okay, so we're going to look at this predicted value in terms of the random variables. Okay, so what's random here? Well, remember we can look at these two parameters, the betas, as random variables, and last time we showed that they have normal distributions. Okay, so we can write like this. Okay, so thinking of it as a random variable, we can look at its mean and variance. Okay, so so let's do an expectation calculation first. So let's take the expected value of this prediction as a random variable. Okay, so by the linearity of the expectation, I can take the expectation on the right hand side. So I have e of beta 0 hat, and x0 is a constant, so pull it out, and then e of beta 1 hat. Okay, and so this is where what we learned in our last lecture comes into play. We learned that beta 0 hat and beta 1 hat are unbiased estimators of beta 0 and beta 1. And specifically, these two guys have normal distributions, mean beta 0 and mean beta 1. So we can use those facts here. So this is simply beta 0 plus beta 1 x0. Okay, so that follows from the unbiasedness. Beta 0 hat and beta 1 hat are unbiased. Okay, so that's where we use our results from last time. So what is this? Beta 0 plus beta 1 x0? Well, if you look, this is exactly what our model for this new value says. Okay, so y0 is normally distributed with this mean, and so these means match up. So in particular, we notice that this is simply the expectation of y0 itself. Okay, so notice this one has the hat, this one does not. This is looking at the model where we have the unknown beta 0 and beta 1. So the model says this should be the expected value of the new observation. Okay, so in other words, we can say that this y0 hat is an unbiased estimate. So this is an unbiased estimate. Well, of what? Well, of the mean. Of the random variable for the prediction. Okay, and so we see that then when we view it as a random variable. Okay, so that is the expected value. So the other thing we will calculate is the variance. So let's do variance y0 hat. Okay, now this one is a little more messy, but the gist of it is actually very similar to what we learned last time. We can get this variance by looking at as a function of existing random variables. Okay, so what do we have to remember from last time? So how do we get the mean and variance of beta 1 hat? Well, we viewed it as a linear combination of the yi's. Okay, and then I also claimed that you can also think of beta 0 hat as a linear combination of the yi's. And so if you put it together, then that means this whole thing, beta 0 hat plus beta 1 hat x0, is itself a linear combination of the yi's. Okay, so so this requires some algebra. I'll give you the expression, and then first, and then I will explain it. Okay, so we get this. The final result is that this is 1 sigma squared, and then inside you have 1 over n plus the prediction, the x value of which we want to make the prediction, x0 minus x bar squared. And the bottom is the sum of squares x. Okay, so how do we get this? Okay, how do we do this? So what happens in this algebra in here? So as I mentioned, but we can get this by expressing y0 hat as a linear combination of the y's. Okay, so I will omit that algebra, but I've explained why that can be done. Okay, so that's the mean and the variance. And so because of this property, we also know that not only is y0 hat having this mean and variance, it is specifically normally distributed with this mean and variance because it's a linear combination of independent, can be written as the linear combination of independent normals. Okay, so this implies that y0 hat is normal with that mean and variance. Okay, so this mean goes in here, and then this variance goes in here. Okay, so that's the estimator for our prediction. Now, we're on our way to calculating what we call prediction intervals. Okay, so if I give you a value of x0, give me an interval with a specified level of confidence in which we would expect the true value of our new data point y0 to fall. And so to do that, let's define one other concept, which is the prediction error. Okay, so we're going to define it as a random variable. Okay, I'm going to write it and then explain. So the random variable for prediction error is I'm going to take the random variable y0, so this is the modeled random variable for the new value, and then I'm going to subtract our predictor as a random variable. Okay, so y0 minus its minus the predictor for it. Okay, so what I need to point out here is that these two are actually independent random variables. Okay, so why is that? So these are independent. Okay, which is going to help when we try to calculate its variance. Okay, so they're independent because we need to remember that this guy, as we just explained, this is a function of our data because we're making our prediction on the basis of the model that we fitted to the data. Okay, so just like I wrote up here, y0 hat is a function of the existing data. So everything in here is all these yi's are independent, and then when you plug in a new value, this y0 for our new observation, then it is also independent of all the previous observations. Okay, so therefore that shows that these two guys are independent, and so that's going to help when we take the variance of our prediction error. Okay, so let's do that up here. Okay, so let's find this mean and variance. Okay, so let's start with, so what's the expected prediction error? So that's E of y0 minus its prediction, y0 hat. Well, we did that already because we can take the expectations of each of these. So we take E y0 and expectation of the predictor. And we already found here that both of those equal beta 0 plus beta 1 x 0. So this is 0. So the average prediction error when we use the value of our fitted regression line, the average prediction error is 0 if the model is correct. Okay, and then the other part is to calculate the prediction variance. So that's variance of y0 minus y0 hat, variance of the prediction error. Okay, so as I argued here, y0 hat is a function of the yi's in the data, and y0 is an independent random variable relative to the other y's. And so I can just use the fact that these are independent random variables, and so we have variance y0, and then plus. Okay, so remember the constant here is -1, so it's going to come outside and square. We'll write that for completeness. So -1 squared variance y0 hat. Okay, and so what is variance y0 hat? So this is the model. This is the model for y0. So this is normally distributed with mean sigma squared. And over here we have the variance of the predictor, which we just found, or that we just wrote down here. So this is the second term. Okay, so sigma squared 1 over n. And then this square term involving x bar and the new value x0. Okay, so again, what do we have here is that this prediction error is again normally distributed, okay, when viewed as a random variable. Okay, why is that? Well, we already said y0 hat is a linear combination of independent normals, and now you're just adding another random variable to this linear combination. So you now have this entire prediction error is therefore itself a linear combination of normals. So not only does it have this mean and variance, it is normally distributed with that mean and variance. Okay, so again, we have a linear combination of independent normals. So you can say that is normal. So y0 minus hat, the prediction error has a normal distribution. The mean is 0, and the variance is this expression. So I can factor out the sigma squared. So I'm going to write it as sigma squared 1 plus 1 over n, and then plus this term here. We should have enough brackets, so sigma squared all this. Okay, so that's a nice normal distribution. Okay, so that's the mathematical result, and so we're well on our way to constructing a prediction. We're going to call it prediction interval, and so we follow a very similar procedure to as we constructed confidence intervals for beta 1. Okay, so I'm going to walk you through the steps for that. So the first thing to note is, again, we can take this expression and we can standardize it. So we can divide by the standard deviation of the prediction error, so that's the square root of this variance. And just like in the case where we looked at doing a hypothesis test and confidence intervals on beta 1, we have a slight problem in that we don't know sigma squared. So again, we're going to have to plug in our estimate, sigma hat here. Okay, and so by similar logic then, what we end up with is a t distribution. Okay, so in particular, when we take y0 minus y0 hat, okay, so I divide by this the square roots of this, but with the estimate of sigma plugged in. Okay, and everything else is just copied down, 1 plus 1 over n, x0 minus x bar squared. Okay, so this expression, okay, if it was just sigma, then this would be a standard normal, but I've plugged in sigma hat, so this is the estimated value of sigma, so this follows the t distribution similar to how we got the t distribution for beta 1, the estimator of beta 1. So t distribution degrees of freedom is n minus 2, as before. Okay, so based on this t distribution, this is where we can get our prediction interval for y0. Okay, before I write down that expression, though, I want to give you some intuition here as to what is this variance. Okay, so you notice there's the variance of prediction error. We notice is basically adding up two things here. So let me give you an intuitive explanation. So intuition for prediction error. Okay, so there are two, we can see they're composed of two terms. Okay, so I'm going to label them here. So here you got one, and then here you got the other one. So I'll call them 1 and 2. Okay, so how can we interpret these two pieces? So the first one, here, let's label them 1 and 2 here. Okay, so where's this sigma squared coming from? Well, it's coming from the model for y0. This sigma squared acknowledges that we want to make a prediction for y0. We have to account for the fact that the model isn't going to fit all the data to begin with. There's expected to be variability around the line, and how much variance is there, specifically sigma squared. So we can call this the sigma squared term. We can call the random error associated with the fact that the line is not going to perfectly fit our data. So we call this random error of the new observation. Okay, so we get a sigma squared from there. The same sigma squared error variance that is part of the linear model. Okay, and then there's this second part now. So I label this number 2. So what is this part coming from? It's coming from the variance of the predictor. Okay, so why does the predictor have variance? Well, the predictor has variance because what's random in y0 hat? There's beta 0 hat and then there's beta 1 hat. So this variance is coming from the fact that our estimates beta 0 and beta 1 themselves have variance. Okay, so that's where the distributions of the estimates beta 0 hat, beta 1 hat come into play. So we can call this this part of the variance coming from the variability in the estimates. So this is from the estimating beta 0 and beta 1. Okay, so therefore when we make prediction, our prediction error accounts for both of those two sources of uncertainty. One from the model uncertainty, that we know that the line doesn't fit the data perfectly, so we build in the variability expected around the line, so that's sigma squared, and then we also have uncertainty in our estimates of beta 0 and beta 1. Okay, so those are the two sources. So that those are the two terms. These are the two sources of uncertainty. Okay, and the other thing I would note here is we have to be a little careful when we do prediction. Okay, so we can't just plug in any value of x0 and expect our result to make sense. It's of course going to be driven by the data. So note. So generally, we don't recommend trying to make predictions outside of the original range of the x values in our data. So let's just write that down. So be careful. That this might not be valid. Prediction might not make sense. If this new value x0 is outside the range of the x's in the data. Okay, so when we do try to plug in an x0 outside the range, another name for that is trying to extrapolate, and so generally that should be done with caution. So we don't arbitrarily try to predict something that's outside the range of the data from which we fitted the model. It will be considered less reliable and sometimes not interpretable. Okay, so that's the inference for prediction. So the last thing I want to write down for this is the actual prediction interval. Okay, so based on this t distribution, we can construct a 1 minus alpha prediction interval for this new data point, y0. Okay, so we're going to use this reference t distribution. So we're going to start with our predicted value, so that's y0 hat, and then we're going to plus minus constant from the t distribution, and then we're going to need the standard error. Okay, so just like before, I'm going to call this whole thing is. Okay, so this is the standard error of our prediction. Okay, so I'm just going to put that in here. So we need sigma hat 1 plus 1 over n. Okay, so we construct our t distribution-based prediction interval in the same way we constructed confidence intervals for beta 1 last time. Okay, so what is this? What is the c here? That is again the 1 minus alpha over 2 quantile. So again, it's the same value from our t distribution of t with n minus 2 degrees of freedom. Okay, so that's how we do prediction using our linear fitted linear regression model. Okay, so just to recap, what we've seen so far is, so we've fitted the regression model, so we estimate beta 0 and beta 1, okay, from n data points. So we get beta 0 hat, beta 1 hat. Last time we computed the distributions of these estimates. Okay, so that accounts for the estimation uncertainty in beta 0 and beta 1. And today we applied those estimates to figure out how we would use this fitted regression model to predict the value of y for a new value of x. And so we derived the distribution for that, and then from that we use the normal theory to get our t-distribution, and then construct a prediction interval for this new value of y using this standard error that we derived for the standard error. Yeah, using the standard error of our predictor. Okay, so I think now it's time to show you an example. So first I'm going to do an example on the board, and then I'm going to go over to the computer and show you how to do this sort of analysis in R. Okay, so to motivate and give you an example, as I mentioned in the first lecture, I spent a few years down in Florida for my first job, and I think one of the first things I don't know, like I told you about alligators, but what else comes to mind when you think about Florida is you might think of, well, it is very warm and people grow a lot of oranges in Florida, and indeed citrus is a very important export. Okay, so over here a little picture of some citrus fruits. That's supposed to be an orange, but it's a little red, so maybe you can call it a grapefruit. So when I went to the grocery store, I expected, well, if Florida produces a lot of oranges, then I should be able to buy them for maybe cheaper, and they should be given it's a local product. Of course, I was a little surprised then when I saw that the oranges that they sell in Florida actually mostly come from California. So they're actually shipped across the U.S. To be sold. And I was naturally a little bit curious. And then after I did a little bit of digging, it turns out, well, what are Florida oranges generally used for? It turns out it mostly goes into orange juice. Okay, and so you wonder why. Well, now you probably understand that the oranges that go into your orange juice are probably of a bit of a lower quality than the ones that are sold to be eaten. So that was a little disappointing, but then now I understand what the oranges in Florida are used for. So next time you drink, I don't know, Tropicana or whatever your favorite brand of orange juice, you might note that the oranges used are actually from Florida, whereas the ones that you buy are probably not. So I found some data from the Florida agriculture website. So I was curious how orange production varies across the state. So I'm going to give you a little introduction to this data set that I'll use. So it's called orange production. This is 2018 data, so fairly recent in the state of Florida. Okay, so I'm going to have two variables here. So my x, I'm going to say is the number of acres used for growing oranges, and then the response y is measured in terms of the number of boxes of oranges produced. And this is measured in thousands of boxes, just to make the numbers a little more manageable. And so this information, x and y, was recorded for each of the counties in Florida. So xi, yi recorded each of 25 Florida counties. Okay, so I will give you a few summary statistics, and then we'll work through a few calculations on the board. Okay, so summary statistics. So there's 25 XY pairs. Okay, so the first summary statistic is we call R, so that's the sample correlation between X and Y in our 25 counties. So this was very high, so 0.964. Okay, so a very strong and positive linear relationship. Okay, correlation is very close to 1. Okay, so I'll give you some other summary statistics and we'll do some calculations with them. Okay, so give you the sample mean of X, so that's denoted X bar, so this was 16,000. So this is the average number of acres used to grow oranges among the 25 counties. Y bar was just under 1,800 thousandths of boxes. Okay, and then two other statistics. Okay, so I'll give you these sum of squares, X. So this is 1,245. Pretty big number, 10 to the power 10. And the sum of the cross terms of XY. Okay, so we'll use these. So pretend we have these summary statistics, and in fact I calculated them from the actual data, which I'll show you in R in just a few minutes. Okay, so from this data we can immediately calculate our regression line estimates. Okay, so first let's use these two values. So from here we can calculate our estimate of the slope parameter, so beta 1 hat. In shorthand, the formula for beta 1 hat can be expressed as the sum of the xy cross term divided by the sum of squares x. So these two statistics give us the slope parameter, so divide s sub xy by the sum of squares x. And so that comes out to be about 0.1167. Okay, so let's remind ourselves of what this number means in terms of interpretation. So this is, firstly, this is a positive slope, which corresponds to the positive correlation between acreage and the amount of oranges produced. Okay, so interpretation then is that the expected number of boxes produced. Okay, so this is our estimate, so we can write is estimated to be. So how many boxes? So this is thousands, so I'll just convert it back to the actual number of boxes. So it'll be about 117 boxes higher. Okay, and so what's the unit? Well, it's per acre. Okay, so this is the expected change in y for unit change in x. So in this case, the unit change in x is 1 additional acre per additional acre. And so that's our interpretation of the estimated slope parameter. Okay, from this data, I can also calculate our estimate of the intercept. So it's beta 0 hat. So according to our formula, that is y bar minus beta 1 hat x bar. Okay, so I have all the summary statistics here. So you plug that in, we get minus 85.3. Okay, and so of course, well, what does this mean? Is it interpretable? Well, not really. Well, because this is, strictly speaking, this is the expected production if there was 0 acres. Well, clearly, I didn't have any counties with 0 acres, so x equals 0 is outside the range of the data that I used to fit the model. So we should not interpret it in that way. Okay, so I'll just write here not meaningful to interpret. Since it's outside, no county has x equals 0 acres. Okay, so we calculate those things directly from these summary statistics I provided here. Okay, so now let me give you a couple other pieces of information, and then we will do a few more calculations. Okay, so use this information. Okay, so now suppose I tell you, okay, so suppose we fitted the model and I tell you, okay, the sum of squares of the residuals is this number, 1.31 times 10 to the 7. Okay, so from this information, so remember what are the residuals are the differences between the values of yi and the fitted regression line. And the sum of squares residual is related, as we learned, to our estimates of the residual variance, sigma squared. Okay, so once we have this information, now we can therefore calculate our estimate of sigma squared. Okay, so what is this? Well, it's the, remember in our notation, it's the sum of squares of the residual, so that's exactly this number, and divide by n minus 2. So we can plug in 1.31, 10 to 7, and then we have 25 observations, so 25 minus 2. So there's about 5.7, 10 to the 5th. Okay, and once we have the estimate of sigma squared, now we actually have enough information to also compute the standard error of the slope parameter. Okay, so that's SE of beta 1 hat. Okay, so our formula from last time said it's sigma hat divided by root of the sum of squares x. Okay, so we calculate that. That comes out to be about 0.00676. Okay, so once we have beta 1's estimate and its standard error, well, next thing we can compute is the t-statistic. So suppose we want to test, so to test the hypothesis of whether this slope is statistically significant. Okay, so whether it is significantly different from 0, indicating that there is a significant linear relationship between x and y. So we test the hypothesis of this slope being 0. We compute our t-statistic and calculate. Okay, so remember the t-statistic is the estimate minus, in this case, well, 0, because we're testing it against whether it's 0 or not, and divide by its standard error. So let's plug in those numbers. So 0.11670676. So this is about 17.3. Okay, and meanwhile, so before we can specifically say something about that number, let's remind ourselves of the underlying reference t distribution. So we need a number, and let's also look up, so we can look up the t distribution value. Okay, and so for example, the 0.975 quantile of the t, okay, and the degrees of freedom is n minus 2, so I need to look up the t distribution 0.3 degrees of freedom. So the 975 quantile of that is 2.07, okay, for comparison. All right, so just to remind you of what's actually going on here, so let me roughly draw a t distribution again. So it's symmetric. Okay, and so let's say this is a t with 23 degrees of freedom. Then what we're saying is that the area under the curve between 2.07 and 2.07, so this part in the middle, would therefore have a probability 95%. Okay, so that's what we mean by this quantile. So remember that the t distribution is symmetric, so that means there's 2.5% on either tail. So of course we don't have to use 95%. It just happens to be the most commonly used value. So I'm just using that to demonstrate. Okay, so what we're saying then is that when the null hypothesis is true, so if it's plausible that the slope is actually 0, then the value of the t statistic can be imagined to be a random number drawn from this t distribution. Okay, so you randomly draw a number from this t distribution where most of the probability falls between about -2 to 2. So it is very, very unlikely that you would see a value of 17.3 if you were to randomly draw a random number from this probability distribution. And so that's exactly the idea behind the hypothesis test. We say that a value of 17.3 is very unlikely to have been drawn from this distribution, and so that's the logic behind rejecting the null hypothesis. Okay, so let's add that note here. Okay, so this number we say is very unlikely to see something this big. To see this for a random draw from T23. Okay, so that's the intuition behind our rejecting the null hypothesis. Okay, so formally then we say that we reject the null hypothesis. Okay, so since 17.3 is greater than this critical value, 2.07, so we reject the null hypothesis. So when we say we reject null hypothesis, we should also always state the level at which we're rejecting. So in this case, I used 1 minus alpha over 2 to be 0.975, so in other words, alpha is 5%. We add alpha equals 5% level. And so to conclude, there is a significant linear relationship linear relationship. Okay, so when we say conclusion, make sure we're specific. So here we're talking about the relationship between acres and oranges produced. So let's say that between acres and oranges produced. Oranges. Okay, so while we're at it, let's also compute a confidence interval and also a p-value. Okay, so a 95% confidence interval for our slope. Okay, so we use our formula, so we take the slope estimate, which I just erased, but it is 0.1167. And then the bounds, so that's the middle of the confidence interval, and then the bounds is the t-value, so 2.07 times the standard error of the slope estimate, so it's 0.00676. And so there is a correspondence between the hypothesis test and the confidence interval. So in that we have a significant hypothesis test at the at the alpha equals 0.05 level, and therefore the corresponding confidence interval, so that's 1 minus alpha, so that's 0.95, is also not going to contain 0. Okay, so this so there's a correspondence between these two conclusions. So if the hypothesis test is significant, then your confidence interval will be significantly different from 0, and vice versa. If this hypothesis is not rejected, when we calculate the corresponding confidence interval, we will notice that 0 is going to fall inside the confidence interval. Lastly, I think I want to calculate a p-value. So, okay, so the p-value for this hypothesis test. Okay, so as we talked about last time, the p-value is the probability of seeing a test statistic as or more extreme as the one computed from the data. And so in this case, the test statistic from the data is 17.3. So of course it runs off the scale here, but imagine I have the value 17.3 here, and then I have a corresponding negative 17.3. So the p-value would refer to the probability of seeing something as extreme if the null hypothesis is true. So in other words, we're calculating the probability inside these two tails of the t distribution, which in this case is very, very small, because 17.3 is we're highly unlikely to see something this big from the t distribution. It was a random number drawn from this distribution. Okay, so the p-value, so let's finish this calculation, is the probability that the absolute value of t with 23 degrees of freedom exceeds the thing that I observed, so 17.3. And so because of the symmetry, I can just calculate the let's say the upper tail and then multiply by 2. So I'm going to write it 2 times the probability that the t with 23 degrees of freedom greater than 17, greater equal to 17.3. Okay, and then as I'll show you in a moment, you can do this in R and get a very, very small p-value. So very unlikely to see that if there was no significant relationship between x and y. So p-value 1.2 times 10 to the minus 14. Okay, and we'll make this stay up. All right, so last thing is to apply what we learned about prediction interval. So let's practice and calculate one. Okay, so predict the output. The number of boxes in thousands. Produced if we had, let's say, 10,000 acres to grow oranges. Okay, so let's use the formula that we derived today for prediction. So the prediction would be beta 0 hat plus beta 1 hat times the new value of x. So in this case, the values are minus 85.3, and then the slope 0.1167 times 10,000. Okay, so it's about 1082. Okay, and so finally, let's make a 95% prediction interval. Okay, so I take, this is the estimate, so 1082, and then plus minus the bounds. Okay, so to get the bounds, we have the value from the t distribution, so that's the same c, 2.07. And then I need to plug in the estimate of sigma, so I need the square root of that number. So what was that number? 5. So I need sigma, so it's root 5.69 and the fifth. And then I also need the roots of the two sources. Remember, there were two sources of prediction error, so it's 1 plus 1 over n. So n here 25. And then I need the new value, so 10,000 minus x bar. So x bar was 16,000, so this is 10,000 minus, so 6133 squared. And on the bottom, I need the sum of squares x. So that was 2.5. Okay, so that is our prediction interval. So if we ask the question, predict, give me an interval, 95% for a prediction of how many boxes of oranges produced by 10,000 acres, then we simplify this and then give you an interval. So to take the minus, that'll give you the lower bound, and then the plus sign that'll give us the upper bound. Okay, and the other thing, the final note here is that we're not. So when we do this sort of linear modeling, we're not saying anything about causation, and I think that's important to note. We're not trying to establish a causal relationship between the variables that we are modeling. We are simply asking the question of how might we describe the relationship between them. So let's just add a note here. We're not trying to establish causation. We're simply trying to understand the relationship and build a model for the relationship. In order to establish causation, typically we need to do randomized experiments, which is covered in some of the other stat classes. Okay, so I am going to hop over to R and give you a quick demo for how to do this analysis in R. So let me just switch the camera real quick and I'll be back. Okay, so I'll walk you through this data set. So this is posted on Learn. So it's called Florida Orange data set. So it's provided as a CSV file. So here I've opened up RStudio. I strongly encourage you to do your analysis in R. As you work in R, RStudio gives you a nice interface which is a little more friendly than just using the R console on its own. Okay, so we're going to start by reading the data into R. So we'll use read.csv. So I'm just going to look at the first few rows using the head command. So you notice there's three variables in this data set. The first is simply the name of the county, and then you have the number of boxes produced, thousands of boxes produced, and then the number of acres used to grow oranges. So you can also look at the end of the data set. So you see indeed there are 25 counties. Okay, so let's run through how we do some of these calculations in R. So first, let's do the scatter plot. So this is taking each of these x and y values. So that's done using the plots command. You simply have to put so this takes as input vectors. So that's $ acres refers to the acres column in this data set, and then boxes refers to this vector of value, 25 values for boxes. So you pair them together, that produces this scatter plot. So there's some basic summary statistics commands. So we simply use the correlation command, mean, and standard deviations. That will give us the values I showed you on the board. So for example, we see that the correlation is about 0.964. Okay, so all these operate on vectors. So there's a mean of the 25 values of the acres variable, and so on. Okay, so on the board I also wrote the sum of squares values, so we can calculate them as follows. So what is sum of squares x? Well, we take each of the x values, subtract the mean of x, so that's x bar, and then we square them and sum them up. So that's how we write this in R. So the sum takes the sum of this as a vector. So you notice R naturally operates on vectors. So when I do this part, is xi minus x bar, and then yi minus y bar, and then simply the multiplication multiplies them element by element, and so by summing this in fact does give me the sum of the xy cross term. Okay, so those are just some manual calculations, and you see the numbers that I wrote for you on the board just now. Okay, so the main function that R has for fitting linear models in the broad general case is LM. So syntax of LM is as follows. So it takes as an argument a formula. Okay, and so the left-hand side and the right-hand side are connected using the tilde symbol. And so just remember y goes first. So you put the y variable and then the tilde and then the formula for the right hand side. In this case, there's only one x variable, so it's just y tilde x. So in this case, our y variable is number of boxes, and then x, the independent variable, is the number of acres. Okay, and so what I've done here is I've just assigned the output of this command and stored this in a variable so that I can reference it later. I just called it lm.1, call it whatever we like. Okay, so we run that, and so that fits the model. And so to get a summary of it, we can plug this fitted model object into a summary command. So I've run that here below. Okay, so let's take a look at this output here and see that indeed corresponds with what we did on the board. So we see there. So pay particular attention to this this block about the estimated coefficients. Okay, so you see there's an intercept term, so this is beta 0, and so indeed we get the minus, this is where we got the minus 85 from, and then we have the estimate of beta 1, that's 0.1167. Okay, and so the standard error we calculate on the board is also here, 0.00676, along with its t statistic, about 17.3. Okay, so down here we also should pay attention to this one, which is the residual standard error. Okay, so R calls it the residual standard error. So this 754.4 is the estimate sigma hat. Okay, so to convince ourselves, we can also compute these ourselves. So I have a few other commands here. So the fitted model object contains a number of other things. So it by default includes a vector of fitted values. So I access that by putting a $sign fitted values. So you can see these are the values of the fitted regression line for each of the 25 observations. And likewise, the fitted model object also contains the residuals. And so these are the EIs that we had talked about. These are the differences between the y values and their fitted values. Okay, so as mentioned, we can calculate the sum of squares residuals. So we can take all the residuals, square them, and sum them up. And if I divide them by n minus 2, that's 23. That is our estimate of sigma squared. And so I take the square root of that. That's the estimate of sigma, so 754.4, and that's exactly what R gives you here in this output as the residual standard error. So this is sigma hat. Okay, and then finally we have values of the t distribution. So to get our values for constructing confidence intervals, we can use the two functions related to the t distribution, q for getting the quantiles, and p for getting the cumulative probability. So q, plugging in the quantile we want, 0.975 with 23 degrees of freedom, gives us the roughly 2.07 that we used on the board. And finally, we can get the p-value. Okay, so to get the p-value, remember we need the tail probability. So 1 minus the probability up to 17.263 is the right tail of the t distribution, and the p-value is to take two times that given the symmetry. So this computes the p-value that we saw on the board, and it's about 1.2, 10 to the minus 14, which is the same value that R's output here gives you as the p-value. So it's indicated probability greater than the absolute value of the t statistic. So very significant relationship. Okay, so I want to end with a quick discussion about some of the points in relation to the model assumptions. Okay, so we'll look at model checking in more detail in the future, but I do want to mention a couple of things while we're on this example. So in particular, if you look at this this plot, you notice that, well, when there's more acres, the output also, in terms of oranges, also tends to be more variable. Okay, so kind of first discussion points. Let me just put it here, is to ask the question, well, is sigma the same for all values of y? And it appears not, in the sense that the variance appears to be higher, and which makes sense. If you have more acres, you will probably have higher variance in the number of boxes produced. So appears not to be, and so as we'll discuss later, this is testing the equal variance or homoscedastic assumption. And so in this case, it appears that sigma would probably be smaller when you have less acres than when you have more acres. So it appears to be violated. And so later when we talk about variable transformations, we can consider doing a transformation. So for example, can consider taking the logarithm as a way to make the errors more similar between the lower end and the upper end of the x range. And the other point, I'll just briefly mention, is that of independence. Okay, so the question we can ask is, are the error terms plausibly independent? In other words, so for example, does knowing, if we know one of the residuals, does that give us information about any of the other residuals? Okay, does knowing one e sub I help predict e sub j for a different county? Okay, so that's what we mean. So in a practical sense, that's what this independence assumption in our linear model says. So if I know the first residual, for example, our first residual is 55, does that give me any information to predict the residual or the error for any of the other counties? And so there's diagnostics for checking that, but intuitively in this case, I mean, you might think, okay, if two counties are close together, then maybe there might be some common factors at play for geographically close counties. So those are the kind of practical questions that we'd be asking when we talk about this assumption for the error terms being independent. Okay, so these are points that we'll discuss a little more when we look at model diagnostics and model checking. So I'll pause just before I end. That covers what I wanted to show you today in terms of finishing up our discussion of simple linear regression. So how to do prediction, and then showing you worked out example both by hand and in R. So pause to see if there are any questions, and then I will sign off. Yes, so I will post the R file. So all this we posted. Data set is already posted, and then the R file will be added to Learn as soon as the lecture is over. So then you can run this analysis yourself as well. So I will post that for you. Okay, if there aren't any other questions, is there practice questions for the quiz? So the quiz will be posted. So at the end of the day, so it will be available for you to take starting at right after midnight on Thursday. And no, there will not be practice questions. All you need to do is review all the materials that we've covered in lectures 1 to 3. There will be two questions. I expect you'll be able to finish them in about 20 minutes. And then you will upload it to CrowdMark in the same way that you would upload an assignment. The only restriction is you need to upload it within 1 hour of opening it. So that will be set on the CrowdMark assignment. Okay, so if there are no other questions, then I'll be back with our next lecture on Monday. And in the meantime, make sure to review the first 3 lectures in preparation for the quiz.